Now that we can experimentally determine what the rate expression or rate law or rate equation is, we're going to use that to try and work out what the reaction mechanism is. And first of all, we're just going to go backwards and look at the different ways it can work. So the idea is you're going to have to come up with some sort of idea on how the mechanism could work. And then whichever one is the slowest one is going to determine how fast the reaction can go. So if it's the first step that's the slow step, we call it the rate determining step. That'll be the order of that reaction will be the order of the entire reaction. Same if the mechanism shows that the second step is the slow step, then the order of this step will also be the same as the order of the overall reaction. Okay, so just to help you explain that a little bit better, so these are bridges and it's slower to get across the thinner bridge. So there's sort of like a bottleneck here or a bottleneck here. So in this one here, we're not going to look too carefully at whether it's right or not. We're just going to look at if it's possible. Okay, so this is just one proposed reaction mechanism, and we're already told that this one is slow and this one's fast. So we're not actually working out that, we're just getting told that. Now we know this is the equation because of experiments, and experiments have given us this as well. And so if we look at this carefully, if this is the slow reaction, then there's one of these plus one of these. It's the one that's going to be slowing the whole reaction down. And that means it's to the order of 2. So if it's just one thing breaking down and this is the slow reaction, this will be to the order of 1. And if there's 2 of them, it ends up causing a quadrupling effect. It's a second order. So that does agree, that slow step does agree with the true rate order, rate expression, rate law, I should say. The fact that CO2 is not involved is explained in here because it's the fast one, it's not the bottleneck. And just as a side note, these are called intermediates. And if you add up all of these reactions here as in Hess's law, you'll find that the NO2 cancels out, the NO3 cancels out. You'll find out that Hess's law adds up to the overall reaction, of course. Otherwise, it's not the right thing. Okay, so we're going to look at those things to determine, okay, that's a possible reaction mechanism. Okay, it's important to remember these are theoretical ideas, and you've got to get creative sometimes. Some terminology to be covered. So at each step, we can label these. So if they're just one thing turning into something like decomposition, it's called unimolecular. Now, most of the times it's 2 things. It can be the same thing, but it's 2 things that have to hit each other. All right, so that's bimolecular. Termolecular is unlikely because 3 things lining up in the correct 3D orientation is not going to happen very easily. Okay, and just a quick review, what are intermediates? We can extract them from the reaction, they're stable. Whereas transition states, we're not quite sure what they are, but we know they must have come together at some point. So the transition states are here. They must have hit each other at some stage and then they went straight to the products. Whereas intermediate states, they're actually stable and we can collect them. Now, in this particular one, you can tell which one's the rate determining step by which one's got the slowest one, which has got the higher activation energy. So it could be a nasty question if they use that, don't tell you any other information besides this graph, and you have to say, oh, it must be the second one that's the rate determining step because it's got a higher activation energy. Okay, that's just some review. So let's look at this now because this is the reaction that we know occurs, and experimentally you could get this or even more than this. So you can see how crazy it is. So you're not going to be able to tell what it is, even from this here. You've just got to sort of guess possibilities and then assess whether that is possible or not. And that's the best you can do. All right, and you'll never know the truth. So with our current understanding and experimental techniques, probably will in the future one day. Okay, so does this one make sense? First of all, through Hess's law, if we add these all up, it adds up to this, which is fine. We're assuming it's not really balanced here. See if any of the others are balanced. If you do Hess's law with that one's that. So this one's actually assumed there's a 2 there. I don't know whether I said this was balanced or not, but let's move on. Okay, so they're saying that the first couple is going to be the initial steps, the slow. The second couple is going to be the second step, slow. So this one here is the slow one, so that's going to determine the order. This one here is an intermediate because it gets used up. And so the rate would be just according to these two. So the rate order, so that's first and first. So that's how we write the order of the rate expression, and the overall order of the reaction will be 2. And don't really care what happens with the fast as long as we get to the end with the right products. Okay, so this is another way the same thing can occur. I've got 2 dashes there already. Oh, that's because I did that last time. Okay, now if this was the reaction, that would be the intermediate that gets used up with B and creates CD, which is fine. And if that's slow, then this is different. This would be A to the second order. Okay, now for this one, we're still with the first one as the slow step. And so that's all that's there. Okay, intermediates are gone and they will cancel out with Hess's law. So it's first order. The rate's just to do with B. Okay, we're going into second step reactions here. So now this is the only one that counts. And so the rate order for that would be AX, but X doesn't exist. It's intermediate. It comes from AB. So we have to rewrite it like that. So that'll be A squared B, third order reaction. Now, I always wonder how fast is this really? And, this has to build up to enough concentration so that this can start working. So I was just thinking in my head then, and is that why we sometimes see a little bit of a lag at some start of some reactions? Next time I do that, hopefully in my mind clicks, and I'll have a careful look at the reaction mechanism. So hopefully I remember that next time I do a reaction that does a little bit of a lag at the start. Okay, moving on. This is another one where the second step is the one that determines it. And so that'll be A to the 2B. Because, hang on, A2B, but we can't have A2 because it doesn't exist. A2 comes from A and A, and so that's A squared B. Okay, so as you can see, it could be anything. We need to know what the rate order is to have an idea of what it could possibly, the reaction mechanisms possibly could be. And so this is possibly the sort of reactions you can get. Pray to the IB gods they don't give you one of these, because it's sort of like make 'em upsies. It's just like whatever. So what's the reaction mechanisms for this? God knows. We're assuming that you're going to knock 2 together and then add the third one. Okay, so we're assuming, God knows what you could come up with. And if that's the case, it's AB. And so we have to assume that this is the slow one, and this is a fast one, and it has to be number 1. That's pretty horrible for a question. All right. The next one's not any better. Okay, so this is the reaction, and that's the rate. So what's the possible rate, or what's the possible mechanism, and which one's the slow one? I was just thinking if it's bent. So these are the 2 ones they want you to come up with. So the fact that I was just thinking, is it possible? So even drawing the structure is difficult. So doing formal charge, this one's the more electronegative. So this is the compound. And I guess if you're the first one, you're trying to expect this to occur, and they collide end on end, and that pops off for some reason. And that might be slow. And if that's the rate of reaction, if that's the reaction mechanism, it would have to be the rate determining step because it's the only one, and that would match this one. So that's cool. So let's go for the first one. Now the second one, I was just wondering whether it was bent or not, because if it was bent, and that nitrogens and oxygens were like this, then it would be difficult for them to line up. So that's how bad this thing is. They never seem to want you to analyze the 3-dimensional likelihood of them colliding. So you have to work out what the Lewis structure and shape is, because that actually matters for end on end or side on side. And you can see how complicated that was to work out the shape, that it was linear. This one here, we haven't taught you radicals yet, but this is a radical which is important because they're highly reactive and they're going to react very quickly with anything they hit. And so the other mechanism was this: get your creativity cap on for coming up with something, from being able to make something up and be the one that they want you to make up. So I'd imagine in any question they will give you the suggested reaction mechanisms, because you could come up with a million different things. You could come up with some intermediates, then you could be here forever. And so that one there, it pops off, which is highly unlikely, because radicals usually take a lot of energy, like UV energy will do in organics, to break off. And so that is slow. So that would agree. That would not agree, because then it would be a first order in KN2O. So that doesn't agree. And the fact then it comes off as a radical, it's going to be highly reactive, and that's going to be really, really quick. And if that was the case, then it would be N2OO, and then you've got to get rid of the O. And that would match the rate. That would match. But it's highly unlikely, because it's not going to be quick. It's not going to be slow. It's going to be really quick. And that's not what the answer is. I think the answer is both of them could be. But realistically, if you do a bit more analysis, it's not. Okay, so however, 2 seems unlikely that oxygen coming off would be quick and radicals react quickly, so that would not be slow. So you're trying to make the second one slow for it to be the one. Okay, all a bit of craziness, right?